Hello everyone, welcome to my lecture. My name is Shamali, Assistant Professor in CS Department SPC. The topic for our discussion today is computer vision and we will begin by exploring its interactions. So today we are going to use the exciting field of computer vision. In a simple term, computer vision is a field of artificial intelligence that trains computers to interpret and understand the visual world. Think of it as a teaching missions to see and make sense of what if sees, just like humans do. The goal is not just to capture an image, but to enable computer to process it, analyze it, and make decision based on it. It is about more than just photography. It's about giving machines a sense of sight. Let's see about some of the brief history. The computer vision is not a new idea. It has a long and fascinating history. The concept first emerged in 1960s with the early experiment at MIT. So where the researchers tried to get a computer to describe what was in a simple block like machines. So progress was slow for decades due to limited computing power. The key breakthrough came in 1990s with the development of more robust algorithms. But the true revolutions happened in the year 2010, that is 2010. This is when a deep learning, that especially the CNN, convolutional neural networks, combined with a vast amount of data and a powerful GPI unlocked here. So the incredible capabilities we see today. The core task of the computer vision, what can computers see? We can break down what is a computer vision system does into several core tasks. Like image classification is the most basic. Giving an image a single label like cat or a dog in machine learning. The object detection is more advanced. It identifies a multiple objects in a scene and draws a bounding box around each one. So the image segmentations take this as a step further, outlining the exact shape of each object pixel by pixel. We can also perform tasks like human pose estimations, which identifies key body points like image super resolution, which enhances the image quality. The computer vision's pipeline is most about the systems follow the pipelines or a series of steps. It all starts with image acquisitions, capturing the image from the camera. Next is like a pre-processing, feature extractions, high-level processing and recognition. So the key concept and the terminology of the computer vision is that to speak the language of computer vision, there are few terms to know: an image in a 2D grid of number, a pixel in a single point in the grid, and its value represents its color and intensity. The resolution in the number of pixels or the features are distinct visual characteristics in an image. Things like corners, textures, and shapes in an image. And finally, an algorithm is a set of rules or the instructions computers follows to make sense of all this data. So why it is difficult, or we'll say about the modern computer or some of the real world applications. So computer vision is no longer confined to research lab. So it's everywhere. It powers the cameras in autonomous vehicles, helping them detect pedestrians and other cars. It's used in medical imaging to help doctor identify tumors or anomalies. So here our own phones uses it for facial recognition and augmented reality apps. So in manufacturing, it's used for quality control and in agriculture. It helps monitor crop health. The list goes on and on, making it one of the most impactful technologies of our time. So what about the futures of computer visions? So what is next basically? The field is advancing at an incredible pace. We are seeing a shift towards more complex and general models that can understand a scene holistically. So the new research is focused on things like 3D visions, where we can understand a scene's depth, and the video analysis, where we can track objects and events over time. As these technologies become more powerful, There are also brings up important ethical considerations around privacy and bias. So the future of computer vision is not just make about the making smartphones machines, but about using this technology responsibly to build a better world. So let's start with what is image processing. So a techniques to perform operations on an image to enhance it or extract information is like a digital dark rooms. So what are the input for this? Takes an image as an input and output either way. Another image or a specific features. There are three types. One is low level, mid level and high level. Low level is like an operation like filtering and enhancement that deal directly with the pixels. Mid-level is operations like segmentations and edge detection that grows or groups pixels into meaningful regions. The high level is operations like object recognition that interrupt the content of the image. So what is the goal is to improve the image quality or to extract useful data. The technical view of these images are treated as a 2D discrete signals in a digital systems. The color models, we process images using models like RGB, like red, green, blue, or HSV use saturation value, and YCBCR used for the videos. The tools used here is a popular libraries and softwares including OpenCV, MATLAB, and Pythons. The libraries basically like PLL or Skirkit images. The image formations or the form is comet like JPG, PNG, PPM or TIFF. So the applications here is a medical imaging, basically MRI scans for enhancement, satellite images and fingerprint matching. So some of the example we can say is like enhancing an old photo to improve its brightness and contrast. So what is computer vision basically is that science of enable machines to interpret and understand visual data from the world. It is giving computers the ability to see. Difference from image processing is that it goes beyond a simple pixel, manipulating by providing meaning and context to the data. It is a what and why behind the pixel. The focus here is a scene understanding, object detections, tracking, and a 3D reconstructions. But subfields like recognition, segmentations, motion analysis, and estimations. Machine learning and AI plays a major role, like deep learning, particularly CNN, convolution neural networks are essential for feature learning and classification. The integration used is maybe in self-driving cars, surveillance, and the robotics. Hardwares like relies on cameras like LiDAR, LiDAR, and various sensors to collect data. What are the tasks like face recognition, land detections, and gesture recognitions? But there are some of the challenges like dealing with occultations, that is, the object blocking others, maybe the changes in the lighting and the variations in the viewpoint, like some of the perception of that image looking. So the example here is a smartphone's face unlocking systems we use day-to-day life. The image acquisitions and digitalization is that what they are. The process of capturing and converting the real world images into a digital format, like capturing images using a sensors or a camera. The process of converting the analog signal from the sensor into the digital form of a pixel. The smallest unit of digital images holding a specific intensity or the color value of the pixel. The resolution here is a number of pixels in the images. For example, 1920 in 2080. The grayscale images used in each pixel as a single intensity value, usually from 0 that is black to 255 that is white. The color images where each pixel has 3 values represented RGB, red, green and blue. The sampling here is a process of selecting a grid of pixels to represent the continuous images, like quantization, assigning a discrete intensity value to each sample pixel. The artifacts or the digital errors like aliasing, that is a jagged edge, and the quantization noise can occur during this process. Example, scanning a printout photo to create a digital file. The basic operations on images, what they are basically the fundamental mathematical and logical operations applied to a pixels. For example, arithmetic operations like addition, subtractions, and multiplications of an image often used for tasks like background, subtractions, or image averagings. So the logical operations like AND or XOR NOT operations on pixel values, useful for creating mask. So image negatives, inverting pixels values by subtracting them from the maximum value, example 255 minus p, creating a negative like effect. The log or the log transforms here is a compresses the dynamic ranges of an images, making detail in a dark region more visible. So the power law gamma transforms used for contrast adjustments, especially useful for correcting images that are too dark or too bright. The contrast session here is expand the range of pixel intensities to use the full available spectrum. The histogram equalization, we can say, to enhance the contrast by spreading out the intensity distributions of the pixel basically. The smoothening here is removing the noise using a filters like mean or a Gaussian filters which blur the image slightly. The sharpening is basically highlighting the edges and fine tuning the details to make the image appear sharper. Example, we can say the removing the noise from the security camera image to make it more clear. The image filtering techniques, what they are is basically using small matrices like kernel to modify the pixel values based on their neighbors. The linear filtering involves convolution or mathematical operations where the kernel slides over the images. Examples like mean and Gaussian filter for blurring the images, and non-linear filtering for filters like median filters, again that do not use convolution networks, but the median filter is excellent for the removing salt and pepper noise while preserving the edges. So the edge reduction filter, where the specified or the specialized filters like Sobel, Previt, and Canny that highlights the boundaries where pixels intensity changes rapidly. So the high pass filters to enhance fine detail and edges, or the low pass filters to blur the image and remove the high frequency noise. The 2D convolutions, the core operations behind the linear filtering where the kernel is applied to image neighborhood. The kernel size will affect the intensity of the filtering effect. Example, a large kernel means a more blurring. The frequency filtering is like operation on the image in the Fourier domain to manipulate the specific frequency. The morphological filters operations like dilations, that is expands shapes, and erosions like shrink the shapes used for the shape based processing. The examples here is the blurring a photo's background while keeping the subject face sharp. So that is a basic examples here. Next one is a geometric transformation. So what they are is basically they can modify the spatial arrangement of a pixel in an image. Like translation is nothing but a shifting the image locations horizontally or vertically. The rotation is like rotating the image around a specific point. Scaling is basically enlarging or shrinking an image or formatting an image. Shearing is nothing but the slanting the image along the axis. Affine transformation is a combination of these basically, which preserves lines and parallelism but not angles or length. The perceptive transformation stimulates the distortions that occurs when viewing an object from a 3D perspectives. The homogeneous coordinates is a mathematical technique that simplifies these transformations by allowing them to be represented as matrix manipulations. The image restriction, the process of aligning two or more images of the same scene used in augmented reality, projecting virtual objects onto real world videos frames. Example like rotating a scanned document to a correct into skews used in editing or in editor view to write. The next one is regarding the feature reductions and description. So basically what they are is that they will be identifying and characterizing key visual points in an image, the corner or the edges, so key visual cues that are stable and repeatable. The Harris corner detector is a classic algorithms for finding corners. The descriptors here is a numerical vectors, example shift, surf, orb, that describes the area around a key point, making it unique and recognizable. So the key point matching here is comparing these descriptor between two images to find the corresponding point for the matching. The scale and the rotations invariance is that the robust descriptors can handle changes in the size and the rotation of an object. What is the application? The object tracking creating panoramas by stitching images together. The edge reductions algorithms like Canny are popular for detecting precise edges. Half transforms are a technique especially designed to detect regular shapes like lines and circles. The template matching is comparing a small image that is a template to a large image to find its location. The optical flow is that detecting the motion between consecutive video frames, like example stitching together multiple arrays drawn images to create a large panorama. But what is the object detections and recognition is the ability to both identify and locate the object within an image. So object detection is to identify multiple objects in an image and draws bounding boxes around them. Algorithms like YOLO and SST are widely used for this. The classification is like labeling a region or an entire image with a specific object type. Deep learning, especially on CNN, are the backbone of a modern object detecting. Models like ResNet or MobileNet are popular. The dataset is used for training these models require massive label dataset like COCO, ImageNet, and Pascal Walk. The real-time detections essentially for applications like autonomous vehicles or automobiles vehicles where speed is critical. The phase directions, especially form of object detecting for finding phases, algorithm like air cascade and retina phase are used in OpenCV's library also. The OCR is for text recognition using NLP to convert the text found in an image into edible text. The transfer learning using pre-training models and adapting it for a new specific tasks, example like a system that detects cats and dogs in a photo and draws a box around each one, just like face detection. The image segmentations it's like dividing an image into meaningful region or the segmentations. The definition for this is the process of grouping pixel with similar features like thresholding, like a simple method where pixels are separated based on whether the intensity is above or below a certain value. The region-based algorithms that grow or merge similar region to form segments, the edge-based using discontinuous intensity, like that is edge, to define the region boundaries, or the clustering, like unsupervised methods like k-mean clustering can be used to group pixel into segments based on color or texture. The watershed algorithms are gradient-based methods that finds regions boundaries by treating the image as a topographic map, or the segmentations like labeling every single pixel in the image with a class. Example: road, car, pedestrians. The insta segmentations identifies the labels and individual instances of an object, even if they are of the same class. Like Mascar CNN is a popular model for this. The tools like OpenCV, as I told before, and SkidCut Images provides functions for segmentations. Examples like separating different organs in a medical scan to analyze their individuality of the individual feature in the body. What are the real world application is that these technologies are used in solve real world problems like medical imaging, enhancing the MRI and CT scans, and ultimately detecting the tumors. The surveillance systems like monitoring public spaces for security using face recognitions and activity detections, or self-driving cars, a core technology for detecting lanes, traffic signs, and other vehicles. The retail analytics like analyzing customer behavior in a stores, like generating heat maps of where people spend the most of the time, or the agricultures where the monitoring crops for health and detecting the diseases using drone and satellite images. Augmented reality overlaying virtual objects onto the real world in a real time. Maybe the biometrics using a face or a fingerprint or iris recognition for security and authentications. It can be used in any banking sector or in a secured way. Robotics is to giving the robot vision to navigate and interact with their environment. The remote sensing is to classifying land use from satellite images. Example: Google Photos automatically detecting its objects. This slide, the introductions to geometric primitives. Today we are going to dive into the fascinating world of geometric primitives and their transformation, the foundational building block of a computer vision. So what exactly are geometric primitives are? So think of them as a basic alphabet a computer uses to read an image. While we see a car sees a collections of points, lines, and curves. We use these simple shapes to describe more complex object. In this slide, you can see the different types where we have a simple point for a specific locations, a line to represent an edge, and a polygon, a closed shape made of lines, like a square or a triangle. We also have curves for smooth shapes. The key takeaway here is that these primitives are used for feature extraction. They allow a computer to find object boundaries and edges. For example, when a system needs to identify a license plate, it is not looking for letters. It's for detecting the rectangular shape, which is a primitive. This is the very first step in making a computer understand what it is looking at. So the next is the coordinate systems in the vision. Now that we know that these primitives are, we need a way to locate them. This is where coordinate systems comes in. We have a few different maps we use. The most basics in the image coordinate system, which is simply the pixel grid on a screen represented by x or y, which is the different from the world coordinate systems, which uses the real world units like meters or feet. The goal of computer vision is often to map objects from the real world onto the image and vice versa. So this is done with a transformation. The key tool we use for this is a homogeneous coordinates. This might sound complex, but it is a simple idea where we are taking a 2D point, says x or y, and turn into a 3D point x, y, or L or Z by adding one Z. This tricks allows us to perform all of our transformations like shifting, scaling or rotation using just one type of mathematical operations like matrix multiplications is a very elegant and efficient way to handle all these changes. So the next slide is about the translation transformation. Maybe let's start with the simplest transformation, that is what is translation. All this does is shift an object from one location to the another without changing its shapes or the size or the orientation. The formula is straightforward. You simply add a value to the x and y coordinate to get the new position defined by the translation vector, maybe a tx or ty. What's really powerful is that we can represent this simple operation with a matrix, like thanks to like homogeneous coordinates, or as you can see the matrix that as one of the diagonal and the translation value in the last column. This matrix is how we will be perform all over the transformation from now on. This is used in applications like panning an image or moving the directed object such as face across the screen. So the next is about the scaling transformation. So scaling, which is how we resize an object, either making it a bigger one or a smaller one. We use scales factors like small x, small y to define how much to resize in each directions. If small x and small y are the same, it is uniform scaling, which maintains the object's proportions. Like zooming in, and if there is a different, it is a non-uniform scaling, which can stretch or squash the object. So again, the magic of homogeneous coordinates allow us to represent this with a simple matrix. This is used everywhere, from zooming in on a map or resizing a logo in an image to the editor. This scaling transformation is a major part in the real-time applications. So the next one is about the rotation transformation. Your rotation is nothing but a process of turning an object around a fixed point, usually the origin. The amount of rotation is determined by an angle, that is a theta. This is one of the most critical transformation in a computer vision. For example, if you scan a document that is slightly titled, a system need to rotate it to properly read the text. So that's a perfect use case of the rotations. The formulas and the matrix on the slide show how we use sine and cosine function to calculate the new coordinates after the rotations. So this transformation is fundamental for tasks like object tracking and alignment. The next is regarding the shearing transformation. Our final fundamental transformation is shearing. So this is a distortion that slants a shape as if you pushed on one side of the box while the other side stayed still. A perfect example is how italic fonts are returned. The characters are slanted under a shear transformation. It is also used in advanced applications like correction or correcting the image skew or in digital art. So the matrix for a shear transformation is shown here. Like note the unlike the others. This is not an angle perceiving transformation, meaning the angle inside the shapes will change. The next one is regarding the affine transformation. It's like combining everything we have learned so far. An affine transformation is a single powerful operation that can perform any combinations of translation, scaling, rotations, and shearing. So the most important property of an affine transformation is that it preserves parallel lines. If two lines were parallel before transformation, they will remain parallel afterwards also. So you can see the general affine matrix on the slide. Like this single matrix can perform all four of the basic transformations we have discussed. So it is incredibly useful for things like image wrapping and correcting a skew document where you need to preserve the parallel lines of the text. So the next one is a perceptive transformation or the projectives. So we have seen in the EG subjects and all. Finally, we have the most advanced transformations, that is a perceptive transformation. This is a key to stimulating a camera's views of the world. So unlike the affine transformation, a perceptive transformation does not preserve parallel lines, just like in a real life, where railroad tracks appears to meet at a single point of the distance, which is parallel lines can now converge. This is what gives an image a sense of depth and is absolutely essential for tasks like 3D rendering and augmented reality. The perceptive matrix is a bit more complex, but it allows us to handle the realistic perceptive distortions. So here the next comes about the homogeneous coordinates and the matrix multiplication. For example, let's bring all these ideas together. We have seen how every transformation from a simple translation to a complex perceptive graph can be represented by a matrix. This is a power of homogeneous coordinates. It provides a single or a unified framework where all transformation are just matrix multiplication. But it gets even better. Like we can concretate transformation. This means if you want to first rotate an object, then scale it, and then move it, you don't need to perform three separate calculations for each one. You can simply multiply all these transformation matrices together to create one single matrix that does all three things at once. So this is a core principle behind graphics engines and a computer visions library like OpenCV that's available in Python libraries. The next is applications and the real world examples. So to wrap up things up, let's look at how these concepts are used every day in today's world. So the phase alignment uses a combination of these transformation to rotate, scales and translate a detected phase to a standard pose. So the license plate rectifications uses a perceptive transformation to flatten the title plate images. In augmented reality, these transformations are used to seamlessly map virtual objects onto the real world surfaces. Stitching the panoramas relies on geometric transformation to align multiple photos into one cognizant images. So the best example of all of this in action is a Google Maps Street View we are using day-to-day life. When you see a continuous street is actually the result of the countless transformations used to stitch together individual photos, creating the illusion of single fluid virtual world that we have seen in the Google Map Streets View. So today we are going to see about the introduction to photometric image formations. Going to explore the photometric image formations, which is a fancy terms for how light interacts with the world and end up as a pixel on a camera sensors. The goal here is to understand why a pixel has a certain brightness value. It is not just a random number, it is a result of three key factors like light source, the properties of the surface it hits, and the camera's response to the light. This field is called the photometric. Help us to create realistic image in computer graphics and even recover 3D shapes from 2D photos. For example, the reason a shiny metal car looks so different from matte painted one is all due to how light reflects off these surfaces. The next is regarding the radiometric quantities. So before we go further, it is important to understand some key terms from the radiometric, the science of the meaning light energy. When we talk about the light, we use a term like radiance, which is a light leaving a surface in a specific directions. That radiance is a total light hitting a surface, and the intensity is a light emitting from a point source. So these are the physical measurable quantities that and our camera sensor as essential, trying to measure the radiance coming from each point in the scenes. So understanding these will help us to build the accurate model of how light behaves in the real world. Let's talk about the illuminations models. So to simplify these complex interactions, we use the illuminations model. These models breaks down the way light reflects off a surface into a components. So the most famous one is a Pong reflections model. Here, which combines the three types of reflections. First one is the ambient light, which is the overall or the uniform light in the scene. Second one is a diffuse reflection, where the light scatters equally in all directions. Think of the matte wall. And the third one is a specular reflections, which is a mirror light reflections that create bright highlights on a glossy surface. By combining these, we can stimulate the realistic lighting effect in a computer graphics. Next, we are going to see about the Lambertine reflected models. So one of the simplest and most widely used models is this, the Lambertine models. This model assumes a surface is perfectly made, like paper or a unglanced ceramic. It reflects light equally in all directions. So the surface brightness depends only on the angle between the light source and the surface itself, not on where the camera is. This is why her made surface looks the same, no matter where you are standing. The model is simple, fast, and often used in a computer vision to estimate the surface shape because we can ignore the camera's viewpoint. The next we are going to see about the camera response functions. So now let's talk about the camera itself. A camera does not just linearly convert the light into a digital value. This relationship is often non-linear, and we describe it with the camera's response function. So this is why the bright scenes can look overexposed and dark scenes can be noisy. To get a visually pleasing image, cameras apply gamma corrections to adjust this nonlinear response. For serious photometric analysis, we often work with the raw images that we capture, which contains unprocessed sensor data, and we need to carefully calibrate the camera to understand its exact response curve. So we have to talk about the color and the photometry. When we introduce the color, things get even more interesting. So our digital cameras uses the RGB filters to capture the red, green, and blue light. The perceived color of an image is not just about its properties, but also about the light source color, or it's a spectral power distribution. This is why a white shirt might look slightly yellow under a tungsten bulb, but still be perceived as a white. Our brains do a great job of maintaining the color consistency, and we have to build similar logic into our image processing algorithm. Techniques like white balance try to mimic this to ensure the colors look naturally regardless of the light. Next, we have to talk about the photometric stereo. One of the most direct application of these principles is a photometric stereo. So this is a powerful technique for recovering the 3D shapes of an object. The basic idea is simple. We have to take the three or more image of the same object from the exact same camera position, but with the light source combining from a different direction each time. By analyzing how the shading changes across the images and assuming the Lambertine surface, we can calculate the precise surface normal. for every single pixel. We can then integrate these normals to reconstruct a detailed 3D model, which is excellent for things like inspecting intricate coin details. The next we have to talk about the shadows, highlights, and the interreflections in the images. So the real world scenes are complicated. While our models are great starting point, they don't always account for complex phenomena like shadows, specular highlights, and interreflections. Shadows can give us important cues about the object's depth, while highlights are bright spots because by the mirror like reflecting. The interreflection is when a light bounces between the surfaces, illuminating the parts of the scenes that would otherwise be a dark. So these features often break simple models, but advanced photometric algorithms can use them to gain an even richer understanding of the scene. What is the high dynamic range that we call as the HDR imaging? In the human eye, you can see a much wider range of the brightness than a single camera exposure can capture. This is where dynamic range or HDR images comes in. By taking multiple images of the same scene at a different exposure settings, one dark, one normal, and one bright, we can combine them to capture the full range of light from the darkest shadow to the brightest highlight. We then use a process called tone mapping to compress this information so it can be displayed on a regular screen, giving us a beautiful detailed photos of the scenes like sunsets, where a standard camera would either blow out the sky or lose all details in the foreground itself. But what are the applications and the challenges of this? So finally, let's look about the broader impact of this field. Understanding the photometric is essential for many applications. It helps us building the robust face recognition systems that are not fooled by changing lighting conditions. It is a key for 3D scanning, where we use light to determine the shapes. In augmented reality, it helps the virtual objects look alike. They actually belongs in the real world. The main challenges lie in the modeling the complex surface properties and dealing with the things like noise and shadows. But as our models and algorithms get better, we can build ever more realistic and intelligent computer vision system. So today we are going to see about the interactions to digital cameras. We are just break down the technology behind the ubiquitous digital camera. At its core, a digital camera is a device that converts a light into electric signals and then store that information as a digital data. Unlike a film camera, that uses chemical reactions, the digital camera relies on the electronic sensors to capture and convert the light. The final image is made up of millions of tiny squares called pixels, and the more pixels you have, the higher the resolution and the detail of your images. This technology has evolved in many forms, from DSLR to the cameras in our smartphones, and it's integrated into a countless devices for everything from the security to the medical imaging. The camera components and their rules. Let's look at the basic anatomy of a camera. The lens is like a camera's eye. It focuses the light from the scene onto the sensors. The aperture is an adjustable opening inside the lens that controls how much light gets in. The shutter is a curtain that opens and closes, determining how long the sensor is exposed to light. The image sensor is the heart of the camera, converting the light into an electrical signal. Finally, the image processor takes the raw data and turn it into a viewable images file, which is then saved into a storage like a SD card. It's a perfect symphony of these components that allows us to capture a single moment in a time. So we have to talk about the image sensors, that is a CCD versus the CMOS. The two main types of the image sensors you can encounter are CCD and the CMOS. While they both convert the light into an electrical signal, they do it in a slightly different way. The CCD sensors are known for producing very high quality images but consume more power. CMOS sensors, on the other hand, are more common in modern devices like smartphones because they are very power efficient and can read data much faster, allowing for iframes rates and features like slow motion video. All sensors are made up of a grid of a tiny light detectors, and the sensor's dynamic range, its ability to capture the detail in both bright and dark areas, is a key measure of its quality. The next we are going to see about the color sensing, that is a base fillers and demosexing. So you might wonder how a sensors which is inherently monochrome captures color. The answer lies in a base filter. This is a mosaic of red, green and blue filters placed over the sensor's pixels. There are more green filters than red or a blue because our eyes are more sensitive to green light. The sensors captures a grayscale images with a grid of color image formations, and then a process called demosaic uses an algorithms to interpolate the missing colors data for each pixel. This clever techniques allows a single sensors to produce a full color images through it can sometimes lead to a color artifacts if not done correctly. So about the camera calibrations, for a serious computer vision work, a camera is not just a point and a shoe devices. It's a precisely calibrated instrument. The camera calibration is a process of determining camera's internal and external parameters. The intrinsic parameters describes the camera's own properties like its focal length and how the lens distorts image. The extrinsic parameters describes its positions and the orientations in the real world. A common way to do is with a checkerboard pattern, which allows us to mathematically correct for the things like lens distortions so that we can get true representations of the 3D world from our 2D images. So let's talk about the image formations and projection. The most common way we model how a camera sees a world is with pinhole cameras models. This is a simplified mathematical models that explains a perceptive projection, the reason why objects farther away appear smaller. So the key parameters here are the focal length, which determines the magnifications and the field of the view, which describes how much of the scenes the camera can see. The size of the sensors also plays a major role in this. So understanding these principles is crucial for everything from creating the realistic computer graphics to performing precise measurement in the scenes. Let's talk about the image quality factors. So when we talk about the good photo, several factors are at a play. Like resolution is a total number of the pixel and determine the level of the detail. The signal to noise ratio, or we call as a SNR, is a ratio of useful image or data to random noise. A high SNR means a clean image. The dynamic range is the ability to capture the detail in both very bright and a very dark areas of a scene. like range in the ability to capture the detail in both a very bright and a very dark area of the scenes. As I told, the sharpness is how well the camera can dissolve fine detail. So all these factors are interconnected and determine the final quality of the image we see. So what about the camera exposure triangle? So exposure, so how bright or a dark a photo is controlled by a beautiful balancing act known as an exposure triangle. The three corners of these triangles are aperture, shutter speed, and ISO. The aperture controls the size of the lens opening and thus the amount of the light. So the shutter speed determines the duration of the light exposure, and the ISO is a sensor's sensitivity to light. You cannot change one without affecting the other. For example, if you want a faster shutter speed to freeze the motion, you will need to increase your aperture or ISO to keep the image properly exposed. It is a vice versa game. So what about the autofocus and the depth sensing? So the modern cameras have sophisticated systems for focusing. The autofocus we call as a AF, which is automatically adjusts the lens to get a sharp images. These are two main types, like phase directions and which is very fast and used in a DSLR, and the contrast direction, which is a more common in compact cameras and find focus where the contrast is highest. In recent years, we have also seen about the cameras uses a TOF, which is a time of flight sensors or even a lasers to directly measures the distance to the object in the scene, giving them powerful depth sensing capabilities for things like facial recognition and augmented reality. But what is the real-time applications of the digital camera in a vision? So finally, it's worth noting that the digital camera has become the primary sensors for a vast range of applications. In autonomous vehicles, cameras are used to detect lanes, pedestrians, and traffic signs. In medical imaging, tiny cameras performs endoscopies in a medical thing or operations. In surveillance, they power motions, direction, and facial recognition plays a vital role. So from the industrial inspection to the augmented reality and a 3D reconstruction, the digital cameras is not just for capturing memories anymore. It is a fundamental tool that allows a machine to see the and interact with the world that we have not cannot be seen in the real eyes. Interactions to point operators. So today we are going to divide or dive into the world of the point operators, a fundamental concept in digital image processing. So what exactly is a point operator? It's simple yet powerful way to transform an image. The key idea is that we are only changing each pixel's value based on its original intensity. We are not looking at its neighbors or any spatial informations. It's a truly pixel by pixel operations. You can think of this as an applying a function t to every single pixel in your image. As the formula shows, g of x comma y is equal to t of or f of x comma y. So where f is our input image and g is a new transform output. The goal of these operators is to improve the image appearance often by enhancing the contrast, brightness, or correcting the intensity level. So because each pixel is processed independently, these operations are incredibly fast and not interactive. So making them perfect for real-time applications. Point operators can be broadly categorized as either linear, like contrast stretching, or a non-linear, such as threshold. There are some common steps in image pre-processing, preparing the image for more complex tasks like segmentations or object detection. A great example of this is taking a grayscale image and using a simple threshold to turn it into a black and white binary images. So next one is identity and negations operators. So let's start with the two of the most basic point operators, the identity and the negations operators. The identity operators is the simplest of all. It's a formula like g of x comma y is equal to f of x comma y. Mean it does absolutely nothing. It leaves the image completely unchanged. While it might seem useless, it's a good baseline to understand how other operators works. On the other hand, the negations operators is a bit more interesting. It inverts a pixel intensity. If you have an image with a maximum grayscale L, the formula is g of x comma y is equal to L minus 1 minus f of x comma y. This flips the lights and the dark areas. Dark pixel become the bright and the bright pixel became the dark. This is particularly useful in the applications like medical imaging or the astronomy. For example, in an X-ray, we often want to highlight the low intensity structures like bone, which appears in a white against a dark background. By negating the image, the bones turn black or the dark, which can improve the perceptions and make the certain features stand out. This operator is fast and only require a single subtraction per pixel, and it's completely reversible, meaning you don't lose any informations. Next is a thresholding. We have thresholding, a powerful nonlinear operators. Its primary purpose is to convert a grayscale image into a binary or a black and white image. So the logic is straightforward. We set a threshold value t. For every pixel, we ask, is this a value greater than t? If the answer is yes, we make the pixel white, that is 255. If not, we make it as a black, that is 0. The formula neatly summarizes this. Pixels become 255 if f of x comma y is greater than t and 0 otherwise. So the thresholding is a crucial step for object segmentations where we need to separate a foreground object from its background. It used in countless applications, from optimal characters recognition that we call as OCR to detecting the barcodes. We have a few types of thresholding, like global thresholding uses a single value for the entire image, while adaptive thresholding uses a different value based on local neighborhood. One thing is to mindful of it is that thresholding can be sensitive to noise, so it's often a good practice to smooth the image first. Despite that, its simplicity and efficiency makes it an excellent tool for enhancing the contrast between a foreground and its background. The next one is a contrastation, that is in a linear manner. So sometimes an image appears too dark or too light because its pixels values are clustered in a narrow range. This is where the contrast stretching comes in. This linear operators improves the contrast by stretching the range of a pixel value to cover a desired output range, typically from 0 to 255. The formula, that is g of x comma y is equal to f of x comma y minus r minimum into L minus 1 divided by r maximum minus r minimum. Takes a minimum of r minimum and the maximum of r maximum intensity values in the original image and maps them to the new output range. This normalizes the intensity, gives the image a more consistent appearance. The contrast stretching is a simple and fast methods widely used in the field like medical imaging and satellite analyzing, where image might be captured under non-ideal lighting conditions. It's important to remember that It does not add any new information to the image. It simply makes the existing information more visually perceptible and easier for a human to interpret. For instance, it can make a low contrast MRI image much clearer. So next one is regarding the logarithmic transformation. While contrast stretching is linear, the logarithmic transformation is a non-linear operators that give us more control. Its formula is g of x comma y is equal to c into log of 1 plus f of x comma y. This transformation is particularly effective for images with a wide dynamic ranges, meaning they have both very dark and very bright areas. The logarithmic curve enhances the dark region by stretching their value out, while at the same time compressing the light that the bright right regions. So this is ideal for images where the most important details are in the darker parts. This process is commonly used in improve the satellite images that might contain both dark forest and brightly lit snow caps. So the nonlinear mapping requires floating point operations. So the output often need to be the rescaled back to the standard of 0 to 255 range. So the next one is a power law that we also known as a gamma transformation. So another powerful nonlinear operation is a power law, or as I told about the gamma transformation. The formula is g of x comma y is equal to c into f of x comma y, function of y. So here the gamma value y is our key control parameters. If gamma is lesser than 1, the transformation brightens the images, or if gamma is greater than 1, it is darkness the images. So this gives us precise control over the overall brightness and the tone of the images. So the gamma correction is a crucial concept in display technology, as it adjusts image to match the nonlinear way the human eye precise brightness. You can use it to fix underexposed photos or to emulate the photographic effect. For examples, a gamma value of 0.5 can significantly brighten an underexposed photos without blowing out the highlights. So the next one is a piecewise linear transformation. Sometimes a single linear or non-linear function is not enough. A piecewise linear transformations offers a flexible solution by using the multiple linear segments to create a custom mapping. Instead of one formula, you define a series of breakpoints. Between each pair of breakpoints, a different linear function is applied. Is allowed you to have fine-grained controls over a specific intensity range. For example, you can stretch the contrast in the middle tones while leaving the very dark and very bright areas unchanged. This is often used for operations like intensity windrowing and can even be used to invert specific segments of the images. Because it involves multiple conditions, it's often implemented using a lookup table for speed. This flexibility makes it ideal for more complex adjustment, such as enhancing the mid tones in a low-high photographs of the person's face. The next one we are going to talk about the mid-plane slicing. Moving on to the different types of point operators. So we have a bit plane slicing. An 8-bit grayscale image is made up of 8 individual bit planes. The most significant bit plane, that is the 7th, contains the most visual informations. But the least significant bit plane, that is the 0th, contains the least as the names. So the bit plane slicing allows us to extract the visualize each of these planes independently. By looking at these planes, we can understand the image structure. For instance, the lower order planes often contains noise, while the higher planes holds the main details. This technique has some interesting applications. It can be used for image compression, where we might discard the less important bit planes. It is also used in a steganography, the art of hiding data within an image, by subtly altering the least significant bit planes. So next one is the histogram equalization. So histogram equalization is a powerful automatic enhancement technique. The histogram is a bar graph that shows the frequency of each intensity value in an image. In an image with a poor contrast, the histogram is often narrow and concentrated in one area. The histogram equalization works by remapping the pixel value so that the new histogram is flat as possible. This effectively spread out the intensity value, enhancing the global contrast of the entire images without needing any manual parameters. It is a very robust and fast, making it a great pre-processing step before tasks like edge detection. So while effective, it can sometimes lead to over the enhancement in certain regions. For this, more advanced versions like CLAE, that is a CLAHE, that is what we call as the adaptive equalizations, which equalizes the histogram in local regions, can be used to improve the local contrast. A classic example of its use is improving the contrast of an old faded passport scan. So these are the things we have seen. Now let's see about the applications of the point operators. So where do we have seen these point operators in the real life or the real world? They're everywhere basically. In medical imaging, they are used to enhance X-rays and CT scans, making it easier for doctors to spot anomalies. So in remote sensing, we can say they uses them to improve the clarity of the satellite imagery, which is crucial for the environmental monitoring. The next one, we can say the document scanning, which relies on the thresholding to separate the text from the background, a fundamental step for the OCR. They are also used in face detection and license plate recognition as a pre-processing steps to normalize and enhance the images. In the video surveillance, a point operators can enhance the low light footage to make it more viewable. Even in a photography, we use them for the contrast and the gamma corrections to improve the visual appeal of our photos. The great example is using a contrast stretching on a low light airport security footage to make it clearer for a security personnel to see what is happening. Point operators are foundational tools that provides a simple yet highly effective way to improve and prepare the image for a wide range of applications. Introductions to linear filtering. We are now moving from point operator to the linear filtering, a core concept in image processing. Unlike a point operators that works on one pixel at a time, linear filtering consider pixel's neighbors to determine its new value. At its heart, linear filtering is a process that applies a linear operations to an image pixels using a small matrix called a filters or a kernel. The primary purpose of this technique is to achieve various effects such as smoothing an image, sharpening it, detecting edges, and reducing the noise. The operation is called convolution, which is a weighted sum of the pixels surrounding values. The output is a linear combinations of the input. These filters are typically two-dimensional and operates over a small or sliding windows, usually 3x3 or 5x5 pixels. Some common filters you have encountered are the averaging filters, Gaussian filters and the Sobel and Laplacian filters for edge detections. A key advantage of a linear filter is that they are simple, fast, easy as well as that is easy to implement. A great example is using our 3x3 averaging filtering to blur an image, which we'll discuss in more in detail. So next we are going to see with the convolution operations. Let's break down the core operations. So convolution is a formula you see g of x comma y is equal to summation of I summation of j, that is f of x plus I comma y plus j into h of I comma j. Explains how it works. We take out our input images, that is f, and a filter kernel h, and at each pixel x comma y we multiply the kernel values by the corresponding pixels values in the image and sum them up to get the new pixel values for the output image G. So a crucial distinction to note is that in true convolution, the kernel is flipped horizontally and vertically before being applied. So in many image processing libraries, however, the term convolution is used to refer to a more straightforward operations called correlations, where the kernel is not flipped. We have used the term convolution as a common image processing sense. So the size of the kernel is usually an odd numbers like 3x3. So there is a clear central pixel. When the kernel reaches the image borders, we use a padding to handle the edge pixels, often by adding a border of a 0 or by replicating the edge pixels. So this is a powerful and versatile operation used for everything from the noise removal to the edge detections. So the next one is the averaging, which means mean filters. So the averaging filters, also known as a mean filters, is one of the simplest linear filters. Its purpose is to smooth the image by reducing the sharp transition between the pixels. The filters assigned equal weight to every pixels in its neighborhood. So for an n cross n kernel, each element has a value of 1 by n of power 2. The 3x3 kernel shows here is a classic examples. So when this filters is convolved with the image, each pixel is replaced by the average of its neighbors. Because it's average out intensity values, this filters acts as a low pass filters, which means it removes high frequency detailed like noise and fine edges. It's excellent for removing the salt and pepper noises, but its major drawback is that it also blurs the edge of the objects, which might be undesirable. So the next one is a Gaussian filter. So the Gaussian filter is a significant improvement over the averaging filters. Instead of giving equal weight to all the neighbors' pixels, it uses a weighted average based on a Gaussian distribution. This means pixels closer to the center of the kernel have a higher weight, while those further away have lesser influence. The formula shown is that h of x comma y is equal to 1 by 2 pi power of 2 and e of power of minus x power 2 plus y of power 2 divided by 2 sigma of power of 2. So gives the weight of each position in the kernel. The key parameter here is a sigma, which controls the amount of blur. A larger sigma results in the wider Gaussian curves and more blurring. Because of this weighted approach, the Gaussian filters produce a smoother results and preserves the edge better than the simple mean filter. It is an isotropic filter, meaning it has the same effect in all directions and is very common pre-processing step for noise reductions before the other operations like edge detections. The next one is regarding the edge detection with Sobel filters. So now let's look at how linear filters can be used for a different purpose. Example, the edge detection. So the Sobel filter is a most popular choice for this. It works by approximating the gradient of the image intensity. The gradient is a measure of how much the intensity changes in a given direction. The Sobel operators uses two kernel, one for the horizontal gradient, that is Gx, and one for the vertical gradient, that is Gy, by convolving the image with these kernels. So we can find areas with strong verticals or horizontal changes in intensity. We then combine these two gradient images to get the overall gradient magnitude. G is equal to the square root of g of x the whole power 2 plus g of y the whole power 2. This filters effectively highlights the strong intensity changes which are typically the edge of the objects. It is often used as a pre-steps for object detection and helps to reveal the shapes details in an image. The next one is a Laplacian filters. So the Laplacian filters is another important edge detection filters, but it's different from the Sobel filters. It is a second order derivative operators. Instead of measuring the changes in the intensity, that is a gradient, it measures the rate of the change of the gradient. This means it highlights the regions where the intensity changes very rapidly, such as edge. The two kernels you see are common examples, one for 4 neighbor configurations and one for the 8 neighbor configurations. An important characteristics of the Laplacians is that it is non-directional. It detects edges in all directions simultaneously. So because it is a second order derivatives, it's very sensitive to noise also. So you typically need to pre-smooth the image with the Gaussian filter before applying the Laplacians to get meaningful results. It's especially useful for enhancing the fine edges and boundaries. The next one is a high pass versus a low pass filter. To understand the linear filters more broadly, it's helpful to categorize them as either a low pass or the high pass. The low pass filters, like the averaging and the Gaussian filters, smooth an image by removing the high frequency details. Think of a high frequency, a rapid changes in the intensity, like noise or the sharp edges. By averaging the pixels, these filters suppress those rapid changes. The high pass filters, like Laplacian I told, do the opposites. They enhance high frequency details by suppressing the low frequency details, which are uniform, smooth regions. So this is why they are great for edge detections and sharpening. An interesting application is combining these two. You can sharpen an image by taking the result of the high pass filters and adding it back to the original images. So next one is a filter kernel design. The beauty of the linear filtering is that you are not limited to a standard filters. You can design the custom kernels for specific effects. The kernel shows here for just a few examples. The sharpening kernels works by emphasizing the central pixel relative to its neighbors, so which boosts the high frequency details. The emboss filters creates here is a 3D, the shadow like effect. Third one is a motion blur kernel can stimulate the movement. When designing a filters, a key consideration is normalization for filters that don't change the overall brightness of the image, like blurring or sharpening. The sum of the kernel's elements should equal to 1. So the custom kernel design is a balance between the enhancing details and the managing noise. So next one is the implementation and optimizations. So the linear filtering is a fundamental operations So it has been highly optimized in modern software. Libraries like OpenCV in Python and SciPy provided efficiency function for these tasks. For real-time processing, like video surveillance, these filters can be significantly sped up using the GPU accelerations with technologies like CUDA for large kernels, a technique called FFT convolution, that is using the fast Fourier transformation, can be much more faster than a direct convolution. Separable filters like the Gaussian can also be optimized by breaking a 2D operation into two faster 1D operations. So these optimizations are crucial for applying the linear filter into large images or the video streams, ensuring that the processing remains fast and efficient. Next one is the application of the linear filtering. So the application of the linear filterings are vast and diverse. Image smoothing is used to reduce the noise in blurry photos. The edge detection is a fundamental step in the roundless computer vision task, such as for the object tracking in a video or for the segmentation letters in a document for optimal characters recognition, what I call as OCR. For the image sharpening can improve the clarity of the blurry photos. In medical imaging, these filters are used to highlight the tumors or the other anomalies. So in photography, they are used for everything from correcting images to creating artistic effect like soft focus. So here the essential linear filtering is a versatile tool for enhancing the image, extracting the features, and preparing the images for more complex machine learning tasks.